Dear students, in this class, we are going to discuss the concept of retarded potentials. Already we have discussed the concept of potentials for electric and magnetic fields in our EMF lectures. Now it is a time for us to develop the relation between these potentials and their sources. For estimating the potentials, there are two types of approaches. One is the heuristic approach. Heuristic approach means logical approach. Logically, you have to write down the equations. And the other approach is Maxwell's approach. In this approach, we have to use Maxwell's equations for estimating the potentials. So let me tell about the heuristic approach first, then we can go for the Maxwell's equations approach. So that's why already you know, in this heuristic approach, which is nothing but a logical approach, it is meant for estimating the equations of these retarded potentials. In order to understand it very clearly, let me recall the concept of the potential of a point charge. So already you know, the potential of a point charge V is equal to Q divided by 4 pi epsilon into R, where R is the distance between the source and the observation point here. In this equation, Q is nothing but a point charge, which is a theoretical charge. That's the reason we have to go for the most practical charge configuration, that is volume charge configuration. You know very well, there are different types of charge configurations like line charge, surface charge, and as well as volume charge. Out of all the charge configurations, volume charge configuration is the most practical charge configuration. That's why in the place of Q, I can write down Q is equal to volume integral rho V into dV. This is the most practical charge configuration. That's why I can write here now the potential V is equal to 1 by 4 pi epsilon is constant integral. In the place of Q, I can write down rho V into dV divided by R. This is the basic equation required for estimating the potential. It is an electric potential. Just now logically we can write down the magnetic potential also. So using this equation as the basic equation, you have to write down the potentials at different points. This is the equation of a electric potential at a distance r from this. Now let me explain this concept using this figure. So if you are taking this one, it is an antenna. Antenna is basically, I already told you in the last classes, it is a conducting material. It is a conducting structure. It is an origin. From the origin, the source is at a distance r dash and the observation point is at a distance r. But our requirement is what is the distance between the source and observation? It is capital R. Capital R is equal to, you can say, R minus R dash. It is R minus R dash. And R is nothing but the magnitude of this. So R is equal to R minus R dash into this. So this is the distance between the source and observation point here. So now just apply this concept to our potential equation. V is equal to 1 by 4 pi epsilon integral rho V into dV by R. Now using this equation as the basis, I would like to write down the equation for the potential function here. Now let me say, what is the potential function here? V is equal to 1 by 4 pi epsilon into integral of rho V into dV divided by capital R. Now the same equation I would like to write for this figure. V potential at a distance. I am observing the potential at a distance r from this origin. So V of R is equal to 1 by 4 pi epsilon naught into, if it is in free space, epsilon naught, otherwise it is epsilon into integral. What is rho V? Rho V is the charge density. This is the charge density. So charge density is a distance r dash from this origin. That's why I can say rho V at a distance r dash into dV dash divided by, what is the distance from the source and observation point? Capital R. That's why I can write like this. But remember friends, it is a potential which varies with the distance as well as the time. For example, if you are taking this is an antenna, and if it is radiating something into the free space like this, the magnitude of this electromagnetic wave depends on two parameters. One is nothing but the time as well as the distance. With respect to distance it changes, as well as with respect to time also changes. So your potential is also like this. Potential is a function of both distance as well as time. That's why I can say V of r comma t is equal to 1 by 4 pi epsilon integral rho v into r dash rho v of r dash comma t divided by r into dv dash. This is the potential equation. It is an electric potential. Similarly, in the similar grounds, I can write down for the magnetic potential also. What is the magnetic potential? In the place of V, I can write down A of r comma t is equal to A of r comma t is equal to 1 by 4 pi epsilon means mu divided by 4 pi. Integral is integral, and here you see charge density is the source for your electric potential. What is the source for your magnetic potential? It is nothing but the current density J. So that's why I can say that J of r dash comma t divided by capital R into dV dash. So these are the equations for the potentials. Remember friends, these potential functions are having a relation with their sources. It is an electric potential, its source is charge density, and it is a magnetic potential, its source is current density. If you understand it logically, this heuristic approach, no need to by heart any type of equations. The only thing is understand it very clearly. These are the potential functions having these relations with their sources. Once you know this, then I can write down here, these are the potential functions V and A at the antenna. So this is an antenna. This is an antenna. At this place I have written the equations for both V and as well as A. A means vector magnetic potential. Now, if you want to write down the equations at a distance r from this, that means at the point P, what may be the variation? Very simple. Can you expect the same equations at the point P? Same equations, but a little bit modification is required. So that's why I would like to tell you, for example, I want to say, this is the antenna. Through this antenna, the electromagnetic waves are releasing like this. The potential at each and every point is not same. It depends on actual distance as well as time also. So that's why whenever you are measuring the potential at the far away distance, at the far point, the potential will be delayed. The potential will be delayed and they will be retarded also. That's why the potential at the far point from the antenna can be called as retarded potentials. I can say that it is a retarded potentials. So that's why I would like to give an example. Sir, how to understand this potential concept? I want to give a small example. Nowadays, everybody is very much interested to go through these IPL cricket matches. Suppose if the match is conducting in Delhi, you are viewing from Vijayawada. Then suppose as soon as the batsman is out, after how much time you can understand that he is out? Immediately you can understand? Or otherwise before that also you can understand? No. Definitely some time, some propagation time is required to understand that he is out. But what is the propagation time? That propagation time is nothing but the total distance from Delhi to Vijayawada divided by the electromagnetic velocity. It is a fundamental relation. What is the time here? Time t is equal to distance travelled divided by velocity. This is the fundamental equation. So that's why in my example I am telling you, the antenna is in Delhi. Let me say it is in Delhi. And the point P is in Vijayawada. Let me say that this is Vijayawada. Then something happens at Delhi. After how much time this person who is in Vijayawada can understand? After some time. How much time? The time is very simple. Time t is equal to the distance travelled r divided by the velocity of the electromagnetic wave. So immediately I can say, friends, the potentials at the point P are delayed by how much time? r by v seconds. So as they are delayed, they are also retarded. That means the potentials are retarded by some amount. Well, how much amount? That amount is nothing but r by v seconds. So using this concept, now I would like to write down these potential equations at the point P here. So how to write down? At the potential point P, at P, I can write down at the point P, both potentials are delayed. Those both potentials means electric potential V of r comma t is equal to 1 by 4 pi epsilon integral rho v at a distance, rho v at r dash comma t, but this t is delayed now by how many seconds? R by v seconds. So that's why t minus r by v divided by r into dv dash. Similarly, a of r comma t is equal to mu by 4 pi integral. This here what is the source? J of r dash comma. How much time is delayed? T minus r by v seconds divided by r into dv dash. So these are the equations which are actually time delayed by how many seconds? R by v seconds, or otherwise you can say they are retarded by some amount. They are retarded by how much amount? R by v seconds. That's why these two equations are called as potentials, delayed potentials. I can say that these are the retarded potentials, which may be also be called as delayed potentials, because they are delayed by how many seconds? R by v seconds. So this is the way of understanding, writing the equations of these potentials using which approach? Logical approach. Logically we are doing this, but if you want to prove it mathematically, then definitely. Now let me continue the next approach, which is also meant for estimating the potential, that is Maxwell's approach. Okay. Just now we have seen the way of writing the equations of the retarded potentials using the logical approach, that is called heuristic approach. Now let us obtain the same equations using the Maxwell's approach. In this approach we have to use the Maxwell equations. So let me recall all the Maxwell equations, those four equations. Del cross H is equal to J plus D dot, that is also equal to J plus epsilon times E dot. This is the first equation. And the second one is del cross E is equal to minus mu into H dot. And the third one is del dot D is equal to rho V. That means del dot of epsilon times E is equal to rho V. Therefore, del dot of E is equal to rho V by epsilon. So this is the third equation. And the fourth one is del dot B is equal to 0. That is del dot mu H is equal to 0. Therefore, that is del dot is equal to H is equal to 0. This is the fourth equation. So these are the four equations you are having. First one is nothing but the Ampere circuit law. This is the nothing but modification of your Faraday's law. And third one is the Gauss law. And the last one is it is the property of a magnet. That means non-existence of the magnetic monopole. So if you take this equation del dot B is equal to 0, and this will be satisfied whenever the vector B is a curl of something, which is nothing but the concept of your magnetic potentials. So let me say the magnetic potential once again by taking that universal equation here. What is the universal equation we have? Del dot B is equal to 0. Del dot B is equal to 0. That means del dot of mu H is equal to 0. B is equal to mu H, you know this. Therefore, del dot H is equal to 0. Del dot H is equal to 0. And this equation will be satisfied whenever H is a curl of something. So that is the equation I am telling you. In the place of B, the scientists have substituted so many parameters. Divergence, curling, as well as gradient, everything they substituted. But this equation is actually satisfied whenever B is a curling of something. So if you take B is equal to del cross A, curl of a vector where A is nothing but a vector magnetic potential, then only this equation is satisfied. So in the place of B, I can write down mu H is equal to del cross A. Therefore, H is equal to 1 by mu of del cross A. 1 by mu of del cross A. So actually, what is the potential here? Vector magnetic potential A, and its source is magnetic field. So it is the relation between source and its function. Its potential function is A and its source is H. That's why it is the relation between magnetic field and its source. This is also the most important equation. Now I would like to substitute this equation into our second equation, del cross E is equal to minus B H dot. So what is that equation? Del cross E is equal to del cross E is equal to minus mu H dot. Okay, minus mu H dot. So from this equation I can write down what is H dot? H dot is equal to 1 by mu into del cross of A dot, because A should be having partial differentiation. And remember friends, dot indicates the partial differentiation with respect to time. So if you substitute here, then you are going to get del cross E is equal to minus mu into, what is H here? H dot here 1 by mu into del cross of A dot. Okay, and mu and mu will be cancelled. Therefore, I can simplify this as, if you take it to the left side, I can say del cross of E plus A dot is equal to 0. This is the most important equation, remember this. Del cross E plus A dot is equal to 0. This is the equation obtained just substituting this equation to our Maxwell's equation. So let it be, this equation is fifth equation. So already we are having 4 equations, and this may be sixth equation, and it may be the fifth equation here. This is the 5 and 6 equations. And remember friends, del cross of E plus A dot is equal to 0. Now it is much more important to concentrate here. When it will be equal to 0 from the vector calculus, curl of something will be equal to 0. Curl of something means it should be having a gradient concept here. Curl of a gradient must be equal to 0. So del cross of del something. So that's why I can write down E plus A dot is equal to curl gradient of something. So I can write here either E plus A dot is equal to, that equation will be satisfied. What is that equation? Equation number 6 will be satisfied whenever it is equal to the gradient of something. Therefore, E plus A dot must be equal to minus del V. It is a potential. So you can say del cross of E plus A dot. E plus A dot means del V is equal to 0. So from this I can write down, you can say that this is E is equal to minus del V minus A dot. This is the most fundamental equation which is required, because the electric field is expressed in terms of electric potential as well as magnetic potential. So E is equal to minus del V as well as minus A dot. So this will be the equation number 7. It is equation number 7. The electric field is expressed in terms of electric potential V and magnetic vector potential A. And here also H is equal to 1 by mu of del cross A. H and E are the fields, and A or V are the nothing but the potentials. So these two equations are telling about the relations between the fields and potentials. In order to develop these two equations, in our two Maxwell equations, we have used the second equation and as well as your fourth equation. These two equations you have used for developing these relations. So these another two equations, the first equation and third equation is meant for developing the differential equations for this. So let me just derive the differential equations using these equations. Now we are going to develop the differential equations using the another Maxwell's equations. What is the first Maxwell equation? Del cross H is equal to J plus D dot, that is equal to J plus epsilon times E dot. What is the electric field equation? Just now we got electric field is equal to E is equal to minus del V minus A naught. This is the equation we got it. Electric field is expressed in terms of electric potential and magnetic potential. Now in this equation I want E dot. What is E dot? E dot is equal to minus del V dot minus A double dot. This is it. Just a substitution. Now, what do you mean by this magnetic field intensity? And already you know, H is equal to 1 by mu of del cross A. Del cross A. This is the definition of this magnetic vector potential. So, if you just substitute these two equations in the above equation, you are going to get the differential equation here. So, how to do this? Del cross H. What is the del cross H? Del cross H means you can say, I can write down del cross H is equal to 1 by mu of del cross of A. This is the equation you have to substitute on the left side. And what is your E dot? E dot is equal to minus del V dot minus A double dot, and in this right portion, and you have to substitute like this. So finally, I can write down here 1 by mu of del cross of A is equal to 1 by mu of del cross of A is equal to, okay. Then what is your E dot here? J plus epsilon times E dot. Epsilon into, I can say epsilon into, what is your E dot? E dot means minus del V minus A double dot, minus A double dot into plus J. This is plus J. So I can write down here epsilon into, this is epsilon into E dot means del V dot minus A double dot. Now he is here. From your vector calculus, what is del cross of A? Del cross of A is a standard equation. It is defined as del dot A minus del square A. This is the equation already in your vector calculus. And substitute here, it is 1 by mu into del dot A minus del square A is equal to epsilon times this one minus epsilon times del V dot minus epsilon times A double dot plus J. So now it can be written as del dot A minus del square A is equal to minus mu epsilon into del V dot minus mu epsilon into A double dot plus mu C. Now I would like to just arranging the terms. I would like to take the terms del square A and mu epsilon into A double dot on one side and the remaining terms on other side. So that can be written as del square A. This is del square A minus mu epsilon into A double dot is equal to del dot A, del dot A plus mu epsilon into del V dot minus mu Z. So this is the differential equation we require for getting the potential functions here. This is the differential equation. So this is the differential equation we got after substitution. Let it be 8. So one more differential equation we would like to produce by taking another Maxwell's equation. You know, del dot D is equal to rho V means del dot epsilon times E is equal to rho V. Del dot E is equal to rho V by epsilon. Just now we have seen what is the value of E? Electric field. Electric field is equal to minus del V minus A naught. This is the equation we got here. Just to substitute this E in this above equation, we are going to get one more differential equation. So del dot of E means what is the V value? Minus del V minus A naught is equal to rho V by epsilon. So del dot of del V, del square V, that means minus del square V minus del dot of A dot is equal to rho V by epsilon. You take minus common on both sides, you can get your del square V is del square V plus del dot of A dot is equal to rho V by epsilon minus. This would be minus. So you are going to get the minus here. So this is one more differential equation we got here, which will be numbered as 9. This is the 9th equation. And remember friends, if you observe in 8 and 9, there are two unknowns. One is scalar magnetic potential, other one is vector magnetic potential. And if you observe closely, these two equations are not going to yield the same solution, because it is depending on two unknowns. And one more thing is, as per the Helmholtz theorem, they can produce a unique solution whenever a vector is specified for both divergence as well as curl. So that's why I would like to just summarize and simplify them using this Helmholtz theorem. And let me see the Helmholtz theorem first. Okay. From these two differential equations, we understood very clearly they are the functions of two unknowns, vector magnetic potential and scalar magnetic potential, and they are not producing the unique solution. So in order to get the unique solution, every vector has to be specified for its divergence as well as curling as far as Helmholtz theorem is concerned. Here, any vector field due to finite source specified uniquely if both the curl and divergence of the field are specified. So already you know H is equal to 1 by mu of del cross A, and this is the definition of your H field. And E is equal to minus del V and minus A naught. And if you are taking this H and electric field here, you know already we have developed one equation. You can say that this is curling of E plus A naught is equal to 0. That means curl of your vector magnetic potential is specified, but its divergence is not specified. But they can produce a unique solution whenever both are specified here, curl as well as divergence. That's why in order to achieve this condition, we should have a small approximation here that is called Lorentz Gauge condition. Del dot of A bar is equal to minus mu epsilon into V dot. So this is the equation which is giving the relation between vector magnetic potential and scalar magnetic potential. This equation is called as Lorentz Gauge condition. Using this Lorentz Gauge condition, we can write the above differential equations in the simplest format. So how can you write down this here? You can write down here, it is for this equation del square A minus mu epsilon into A double dot is equal to minus mu Z. The next equation is scalar magnetic potential del square B minus mu epsilon into V double dot is equal to minus rho by epsilon. So the potentials are here related with their sources. Related with this, here magnetic potential is related to its current density and scalar magnetic potential is related to its charge density. So these are the simplified second order differential equations after using the Lorentz Gauge condition. And already you know how to write down the solution for the differential equations here. What are the solutions for the differential equation? It will be having two unknowns and you can write down the solutions here. And if you see it closely, these are nothing but your Laplace's equation, second order equations. So for this, happily using your own techniques, happily you can write down the solutions here. That is A of r comma t is equal to A of r comma t is equal to mu by 4 pi integral. What is this? This is j of r dash comma t divided by r into dv dash, and the t will be delayed by r by v seconds. This is. Similarly, your v of r comma t is equal to 1 by 4 pi epsilon integral. What is this? For v, it is charge density rho of r dash comma t minus r by v divided by r into dv dash. So these are the two things are nothing but the solutions of your second order differential equations. So these are the solutions for this second order differential equations. So that's why I would like to tell you, writing the solutions for the second order differential equations is so logical, and it is very easy to write these equations using your heuristic approach. But in the Maxwell's approach, you have to take some strain to substitute one in another, and you should know about your Helmholtz theorem, and you have to know the definitions of the Lorentz Gauge condition also. So here also we have estimated the potentials of the retarded potentials. So for estimating these retarded potentials, there are two approaches. One is logical approach, which is nothing but your heuristic approach, and other one is nothing but your Maxwell's approach. Okay, now we are going to see the potential functions variations for sinusoidal time variations. We have developed these potential equations, and these are the two second order potential equations. This is for vector magnetic potential A, and this is for scalar electric potential. These two equations are developed by using the concept of Lorentz Gauge condition. Now I would like to apply these equations for sinusoidal time variations. What do you mean by sinusoidal time variation? Already in EMF I told you, wherever there is a time derivative dou by dou t, it should be replaced with j omega. So here there is a time derivative for this and this. So two derivatives are here. That's why I can say, in the place of a, I can write down dou square a by dou t square means j omega square, and b means here also you can say j omega whole square. So j omega whole square means j square omega square. J square means minus 1. Minus of minus becomes plus. So that's why I can write down here, it becomes del square a plus omega square mu epsilon is equal into a is equal to minus mu j. Similarly, del square v plus omega square mu epsilon into v is equal to minus rho by epsilon. So these are the two equations actually meant for the sinusoidal time variations. Now just come to the fundamentals once again. Take a antenna like this. This is an antenna, and where the current density is J here, and this is the point of origin. I would like to take a small element of this antenna which is at a distance r dash here, and this is the origin, and at a distance r I am calculating this radiation, the point P here. The distance from this to this is the capital R is equal to r minus r dash. Now here the potentials are we are developing here, and we are measuring the potential at the point P. Whenever the electromagnetic sphere coming from this to this, the magnitude may be same, but definitely because of the path difference, and they will be having a phase difference here. How much phase difference you can expect? The phase difference will be given in terms of an angle of exponential e to the power of, it should be e to the power of minus j beta into, what is the distance here? Capital R here, capital R here. So for the sinusoidal time variations, if I want to write down the potential equations at the point P, happily we can write down here. You can say that A of R is equal to, of course time I am omitting here, A of R is equal to mu by 4 pi integral, what is the potential basis here? Electromagnetic potential. So vector magnetic potential basis is, you can say that current density J at a distance r dash into e to the power of minus j beta r, which is the phase angle. divided by capital R into dV dash. Similarly, V of R is equal to 1 by 4 pi epsilon integral, I can say this is rho of R dash divided by R into e to the power of minus j beta into R into dV dash. So friends, understand it very clearly. The only one factor that comes into the picture, it is nothing but e to the power of minus j beta R. Why it is coming here? It is a phase difference that is coming. Whenever you are applying the sinusoidal time variation at this point, by the time they reach this destination, they should be having a phase difference. So in this way, you have to write down the equations for the sinusoidal time variations also. So for estimating this retarded potentials at any point, there are two types of approaches. One is heuristic approach and other one is your Maxwell's approach. Maxwell's approach is somewhat lengthy, but you have to have a patience to understand it. So whatever it may be, if you do a practice or 2 or 3 times, it will be very easy to write it. Okay. I hope you understand this lecture very well. Thank you.